2016, the residents of a small town in Michigan got a letter from their local government telling them not to drink the water, not to cook with it, not to give it to their children or their pets. The water coming out of their taps looked perfectly clear. It had no smell. It had no taste. Nothing about it seemed wrong at all. But inside that water, at concentrations too small to see, too small to taste, too small to detect without laboratory equipment, was a family of synthetic chemicals that had been building up in the groundwater beneath their community for decades. Chemicals that do not break down in the environment. Chemicals that do not break down in the human body. Chemicals that had been used in products that almost every American touched every single day, from the non-stick pan on the stove, to the fast food wrapper on the kitchen table, to the waterproof jacket hanging by the door. The town was called Parchment, but it was not alone. Not even close. In the years that followed, testing programs across the United States and then across the world began finding the same chemicals in water supplies in hundreds of communities, in rivers and lakes and streams, in rainwater collected in the most remote locations on Earth, far from any factory or military base or industrial site. Scientists found them in the blood of polar bears in the Arctic, in fish in mountain lakes that had never been touched by industry, in the umbilical cord blood of newborn babies. These chemicals had a name. They were called PFAS, perforf, and polyfluoroalkyl substances, and their story is one of the most remarkable and troubling chapters in the history of industrial chemistry. Because PFAS were not an accident. They were not a byproduct that nobody noticed. They were developed deliberately, celebrated as one of the great triumphs of 20th century science, and then used in thousands of products for decades, while the companies that made them quietly gathered evidence that something was going very wrong. The story begins in the 1930s in the research laboratories of one of the largest chemical companies in the world. DuPont, based in Wilmington, Delaware, had built its reputation over more than a century on making materials that did not exist in nature. Nylon, neoprene, freon. The company's chemists were extraordinarily good at finding entirely new molecules and figuring out how to make them useful. In 1938, a young DuPont chemist named Roy Plunkett was working on developing new refrigerant gases. He had been storing a gas called tetrafluoroethylene in pressurized containers, and one morning he opened a container that should have been full and found it was nearly empty. Instead of a gas, there was a white, waxy solid coating the inside of the container. The gas had polymerized. Its molecules had spontaneously linked together into long chains and formed a new substance. Plunkett poked at it, tested it, and quickly realized it was unlike anything he had ever encountered. The white solid was extraordinarily slippery. Nothing seemed to stick to it. It was chemically inert, meaning it would not react with almost any other substance you tried to mix it with. It was stable at temperatures that would destroy most other materials. And it was an excellent electrical insulator. DuPont patented the material in 1941 and eventually gave it a brand name that became one of the most recognized words in the American kitchen. They called it Teflon. The chemical name was polytetrafluoroethylene, or PTFI, and the key to understanding everything that came after is understanding what made Teflon so exceptional. The properties that Plunkett had stumbled onto were not accidental. They came directly from the chemistry of the carbon-fluorine bond, the connection between carbon atoms and fluorine atoms that formed the backbone of the molecule. The carbon-fluorine bond is one of the strongest chemical bonds that exists in nature. Fluorine is the most electronegative element on the periodic table, meaning it holds on to electrons with extraordinary force. When fluorine atoms surround a chain of carbon atoms, as they do in PTFE, They create a kind of chemical armor around the carbon backbone. The fluorine atoms are packed so tightly and hold on so firmly that almost nothing can penetrate the outer shell. No solvent, no acid, no base, no grease, no oil, no water. They all slide off. The molecule simply will not engage with the outside world. It was this incredible stability that made PFAS so useful, and it was this same incredible stability that would eventually make the entire family of fluorinated chemicals a global environmental problem. Because a molecule that will not react with acids or solvents or temperatures that destroy other materials also will not react with the biological processes inside living organisms. It will not react with the bacteria and fungi in the soil that break down organic material. It will not react with sunlight and oxygen the way most synthetic chemicals eventually do. PFAS and the family of chemicals related to it were not just stable under the conditions of everyday use. They were stable under almost every condition that nature had available to break things down. They persisted, indefinitely. Scientists would eventually give them a nickname that captured this perfectly. They called them forever chemicals. After the Second World War, the chemical industry expanded at a pace that had no precedent in history. Plastics, synthetic fibers, adhesives, coatings, pesticides, pharmaceuticals. New materials were being developed and deployed at a rate that far outpaced anyone's ability to understand their long-term effects. In this environment, fluorinated chemistry became a rich area of research. Chemists at DuPont and at the Minnesota Mining and Manufacturing Company, which most people know simply as 3M, discovered that you could make many different useful molecules by varying the length and arrangement of the fluorinated carbon chains. Different molecules had different properties. Some were extraordinarily effective at repelling water. Others repelled oil and grease. Some were stable as solid coatings. Others could be dissolved in water and used as surface treatments. 3M developed a process called electrochemical fluorination in the late 1940s that allowed chemists to produce a wide range of perfluorinated compounds efficiently. From this process came a product that 3M would sell under the brand name Scotchgard, a spray treatment that could make fabric repel water and stains. Launched in 1956, Scotchgard became enormously popular for treating upholstered furniture, carpets, and clothing. At the same time, DuPont was developing new applications for fluorinated chemistry in its own laboratories. The non-stick coating that made Teflon famous required specialized manufacturing to apply to cookware. But once DuPont figured out how to bond it to aluminum, the non-stick pan became a staple of American kitchens through the 1960s. By that point, fluorinated chemicals were also being used in food packaging, the grease-resistant coatings inside fast food boxes and microwave popcorn bags. They were being used in firefighting foam, a product that the military and civilian firefighting agencies adopted because it could suppress fuel fires with extraordinary speed and effectiveness. They were being used in waterproof clothing and outdoor gear, in carpets and upholstery, in stain-resistant treatments for clothing, sold by the yard at fabric stores, in the lining of pipes, in industrial lubricants, in the coatings of wire and cable. The list of applications grew year after year throughout the 1950s, 1960s, and 1970s. And with each application, fluorinated chemicals entered a little more widely into the world. They were used on military bases across the country, where the firefighting foam, called aqueous film-forming foam, or AFFF, was sprayed in enormous quantities during training exercises. The foam ran off into the soil. It soaked down through the ground. It reached the groundwater. And because these chemicals did not break down, they simply stayed there, accumulating with every training exercise, year after year, for decades. what the companies making these chemicals knew about their health effects, and when they knew it, is a question that took decades of legal discovery and document releases to begin to answer fully. The picture that eventually emerged was not flattering. 3M began conducting internal studies on the toxicity of perfluorinated compounds in the late 1970s. What they found was not reassuring. Animal studies showed that these chemicals accumulated in the blood and organs of exposed animals. They didn't get excreted efficiently. They built up over time. Further studies showed effects on the liver and the immune system and the thyroid. By 1981, 3M's own researchers had found that the compounds were present in human blood samples, including samples from people who had no known occupational exposure to the chemicals. Somehow, the chemicals were getting into ordinary people who had no direct contact with the manufacturing process. The company's own documents from this period showed that internal researchers raised concerns. Those concerns did not translate into public disclosure. The documents were not shared with regulators. The research was not published in scientific journals. It stayed inside the company. DuPont had its own set of internal discoveries that followed a similar pattern. DuPont manufactured a fluorinated compound called perfluorooctanoic acid, known as PFOA, which was used as a processing aid in making Teflon. PFOA was not present in the final Teflon product itself, but it was used during manufacturing, and it ended up in the air and water around DuPont's manufacturing facility in Parkersburg, West Virginia. Beginning in the 1980s, DuPont's internal monitoring found elevated levels of PFOA in the drinking water of communities near the plant. The company's own health studies found elevated rates of certain health problems among workers who handled the chemical. Internal documents showed that DuPont researchers understood that PFOA was building up in human blood, that it was present in the blood of workers' family members who had no direct contact with the plant, and that it had crossed into the blood of a developing fetus during pregnancy. None of this was shared with the public. None of it was reported to the Environmental Protection Agency as required under laws that obligated companies to disclose information about the hazardous nature of chemicals they produced. Instead, DuPont negotiated with the EPA in 2004 to address concerns about PFOA without admitting any wrongdoing, and continued producing and using the chemical for years afterward. The person who ultimately forced some of this information into public view was not a scientist or a regulator. He was a lawyer from a small firm in West Virginia named Robert Bilott. Bilott had been contacted in the late 1990s by a farmer near Parkersburg whose cattle were getting sick and dying in ways that local veterinarians could not explain. The farmer, Wilbur Tennant, had land that bordered a DuPont landfill where the company had been dumping fluorinated waste. Bilott agreed to look into the case, expecting it to be resolved relatively quickly. What he found when he began requesting documents from DuPont was a paper trail that would consume the next 2 decades of his career and eventually lead to one of the most significant environmental settlements in American legal history. Bilott discovered that DuPont had been conducting extensive internal research on PFOA for decades. He found evidence that the company knew the chemical was present in the local water supply and had not told the public. He filed a lawsuit on behalf of approximately 70,000 people in the area who had been drinking the contaminated water. And in 2005, a scientific panel convened as part of the legal settlement found a probable link between PFOA exposure and 6 health conditions, including kidney cancer, testicular cancer, thyroid disease, and ulcerative colitis. DuPont eventually settled the lawsuits for approximately $670 million without admitting liability. The story of Robert Bilott and Wilbur Tennant was eventually told in a 2019 film called Dark Waters, which brought public attention to the PFAS issue in a way that years of scientific papers hadn't managed to achieve. But the legal battles in West Virginia, as significant as they were were only the beginning of a much larger reckoning. By the time the Parkersburg case was being resolved, scientists were beginning to understand the true scale of PFAS contamination. The compounds that had been studied most closely, primarily PFOA, and a related compound called PFOS, which was the active ingredient in 3M's Scotchgard, were just two members of a chemical family that numbered in the thousands. As testing methods improved and became more widely available, the picture that emerged was staggering. PFAS had been found in the drinking water of an estimated 200 million Americans. They were present in virtually every waterway that had been tested in the United States. They had been found in rain samples collected in Tibet, in the Sahara Desert, on the peak of Mount Everest, and on the ice sheets of Antarctica. Scientists who set out to find a location on Earth where PFAS were not present struggled to find one. The chemicals had spread through the global water cycle, evaporating, traveling through the atmosphere, falling as rain, until they had saturated the planet in a way that no pollution source could fully account for. Even if every factory that had ever made a PFAS compound had stopped operating immediately, the chemicals already in the environment would continue circulating through the water cycle for an indefinite period. There was no cleanup plan that could address contamination at a planetary scale. The most promising approaches, filtering contaminated drinking water through activated carbon or specialized membranes, could protect people from the contaminated water coming out of their taps. But they could not remove PFAS from rivers and lakes and groundwater aquifers and soil. They could not remove them from the food chain, and they could not remove them from human blood, where PFAS had been accumulating since the chemicals first entered widespread use in the 1950s. Studies of blood samples from the general American population showed that PFAS were detectable in the blood of virtually every person tested. Studies of archived blood samples showed that concentrations had risen steadily from the 1950s onward, peaking sometime around the early 2000s and declining somewhat in subsequent years as the most widely used compounds were phased out. But declining from a high level was not the same as going away. PFAS were still present, still accumulating, still being ingested every day through drinking water, through food grown in contaminated soil, through food packaged in PFAS-coated materials, through the use of countless consumer products that still contained them. The health science around PFAS took decades to develop into a clear picture, partly because the effects were subtle enough not to show up obviously in individual cases, and partly because the most affected populations were not always easy to identify and study. What the research eventually established was a set of associations between PFAS exposure and health outcomes that were consistent enough to attract serious scientific concern. The chemicals interfered with the endocrine system, the network of glands and hormones that regulate a remarkable range of bodily functions, from metabolism to reproduction to immune response. Studies found associations between PFAS exposure and changes in thyroid hormone levels, with altered cholesterol levels, with reduced effectiveness of vaccines, meaning that people with higher PFAS levels in their blood showed smaller immune responses after receiving standard childhood immunizations. Studies found associations with elevated risks of certain cancers, with high blood pressure during pregnancy, with reduced birth weight in newborns, with delays in puberty, with reduced fertility in both men and women. The effects were not dramatic in the way that acute chemical poisoning is dramatic. No one collapsed immediately after drinking water that contained PFAS at the levels found in contaminated communities. The effects were statistical, meaning they showed up as elevated rates of health problems in exposed populations compared to unexposed populations, effects that were real and measurable, but that played out over years and decades rather than hours. This made them genuinely difficult to communicate to the public because people understand dramatic individual cases far more easily than they understand population-level statistical risks. But statistical risks that affect hundreds of millions of people are not small risks. They are, in aggregate, an enormous burden of preventable illness. The regulatory response to the growing body of evidence was slow and contested. The EPA had the authority to set legally enforceable limits on contaminants in drinking water, but doing so required going through a lengthy process of scientific review, risk assessment, and public comment that could take years or decades. Industry groups challenged the science at every step, funding their own research and arguing that the evidence of harm was not strong enough to justify costly regulatory action. For decades, there was no federal legal limit on PFAS in drinking water. States began setting their own limits, which varied widely. Some communities that knew they had contaminated water had no legal obligation to tell their residents. Some communities that had contaminated water did not even know it, because no one had tested for it. The gap between what the science was showing and what the regulatory system was doing remained wide for a remarkably long time. That began to change in the early 2020s. In 2024, the EPA finalized the first federal enforceable limits on 6 PFAS compounds in drinking water, a step that had been anticipated for years and that represented the most significant regulatory action on PFAS in the history of the United States. The limits set for the 2 most studied compounds, PFOA and PFOS, were 4 parts per trillion. To put that number in perspective, 4 parts per trillion is the equivalent of 4 drops of water in an Olympic-sized swimming pool. The standard was not universally celebrated. Some scientists argued it should have been set even lower. Industry groups argued it was not scientifically justified. Water utilities worried about the cost of treatment systems needed to meet the standard. But as a marker of how seriously the regulatory system had come to take the PFAS problem, the new limit was unmistakable. Outside the United States, the PFAS story followed a parallel but somewhat different trajectory. In Europe, regulatory action on the most hazardous PFAS compounds began somewhat earlier, driven in part by the precautionary principle, the idea that when evidence of harm exists, action should not wait for certainty. The European Union began restricting PFOS in 2006 and moved toward a broader approach to PFAS regulation in the early 2020s, with proposals to restrict the entire class of chemicals rather than addressing them one compound at a time. This approach, regulating the entire chemical family rather than playing whack-a-mole with individual compounds, reflected a lesson that regulators had learned painfully over the preceding decades. When PFOS was phased out, manufacturers replaced it with other PFAS compounds that were initially assumed to be safer because they had shorter carbon chains. These newer compounds, called short-chain PFAS, did indeed appear to be less persistent in the human body, but they turned out to be more mobile in the environment, spreading more easily through water and reaching groundwater more quickly. And some of them showed their own set of concerning health effects. The pattern of replacing a restricted PFAS with another PFAS had repeated itself enough times that regulators began to recognize it as a structural problem rather than a series of individual missteps. The chemical family itself was the issue, not just particular members of it. The manufacturers who had developed and sold these chemicals understood this dynamic from the inside. Documents released through litigation showed that internal research programs had identified health and environmental concerns about successor compounds before those compounds reached the market. The cycle of restriction and replacement had been anticipated and in some cases prepared for. The phrase that appeared repeatedly in legal documents and internal communications was regrettable substitution, the replacement of one problematic chemical with another that turned out to be similarly problematic. It was a phrase that captured, with remarkable precision, the way the regulatory system had been used as a series of speed bumps rather than a fundamental barrier. What does it actually mean to clean up PFAS contamination? The answer is one of the most challenging problems in modern environmental engineering, and it does not have a satisfying resolution. For drinking water, the technology exists to remove PFAS effectively. Granular activated carbon filters can capture PFAS molecules as water passes through them. High-pressure membrane systems called nanofiltration and reverse osmosis can remove them even more efficiently. Ion exchange resins, materials that chemically attract PFAS and hold on to them, are also effective. The problem with all of these approaches is that they generate a concentrated PFAS waste stream. The chemicals are removed from the drinking water, but they have to go somewhere. The concentrated material ends up in a filter medium, or a membrane, or a resin that eventually has to be disposed of or regenerated. Disposing of it safely is its own challenge, because landfilling concentrated PFAS materials risks leaching them back into groundwater, which was the original problem. Incinerating them at high temperatures can destroy them, but requires sustained temperatures above 1,000 degrees Celsius, and if the incineration is incomplete, it can release other hazardous compounds. For groundwater and soil contamination, the options become significantly harder. Pump and treat systems, pumping contaminated groundwater to the surface, treating it, and then releasing or re-injecting it, can work but are extraordinarily slow and expensive over the scale of years and decades. Some researchers are exploring the use of electrochemical processes that can break the carbon-fluorine bond directly, essentially destroying the PFAS molecules in place. Others are working on biological approaches, finding or engineering microorganisms that can break down fluorinated compounds. These approaches are promising, but not yet ready for large-scale deployment. The most honest assessment of the PFAS cleanup challenge is that for surface contamination that is well-defined and well-contained, meaningful remediation is possible, but expensive. For the diffuse contamination that has spread through groundwater over large areas, and for the planetary scale contamination in rainwater and remote environments, there is no known remediation strategy. The contamination that is already in the environment will persist for a period of time that cannot be accurately estimated, because the persistence of PFAS under real-world environmental conditions has been studied for only a few decades, and the chemicals appear to be so stable that the period of persistence may extend far beyond what any current study can measure. The contamination that is in human blood will diminish over time as exposures are reduced. But the half-life of some PFAS compounds in the human body is measured in years, and reducing exposures to near zero requires eliminating sources that are not yet fully identified or regulated. In the midst of all of this, the industries that depend on fluorinated chemistry are confronting a genuine problem that has no easy answer. PFAS are not just used in consumer products that people could theoretically live without. They are used in applications where their unique properties are genuinely difficult to replace. The semiconductor industry uses specific fluorinated compounds in the manufacturing of computer chips, the same chips that power every smartphone, laptop, electric vehicle, and piece of medical equipment produced today. Fluorinated materials are used in the production of solar panels and wind turbines. They are used in the insulation of cables in aircraft and in medical devices. They are used in the membranes of fuel cells, which are one of the most promising technologies for producing clean energy from hydrogen. In many of these applications, alternatives either do not yet exist or have not been tested enough to be confident that they will perform reliably under demanding conditions. The phase-out of PFAS in consumer products, food packaging, cookware, carpets, clothing, is technically achievable and is already well underway in many markets. The phase-out of PFAS in critical industrial applications is a far more complex problem that will require significant investment in materials science research and in validating the performance of alternative materials under real-world conditions. This does not mean it cannot be done. It means it will take time and resources and a level of coordination between industry, regulators, and researchers that has not always been characteristic of how chemical regulation works. The history of PFAS offers some uncomfortable lessons about how that coordination has failed in the past. A chemical family was developed and deployed on an enormous scale before anyone fully understood what would happen to it in the environment. Evidence of harm accumulated inside companies and was not shared with the public or with regulators. When individual compounds were restricted, they were replaced with other members of the same chemical family that turned out to have similar problems. The regulatory system moved slowly while the contamination spread widely. And by the time the scale of the problem was publicly understood, it was too large and too diffuse to be solved with any available tool. The people who live near contaminated sites, the communities around military bases, around manufacturing facilities, around airports where firefighting foam was used in training, did not cause this problem. They did not choose to have these chemicals in their water. Many of them had been drinking contaminated water for years or decades before anyone told them. Some of them had already raised children on that water. The anger in these communities is not abstract. It is specific and personal and entirely understandable. And it has driven some of the most important legal and regulatory developments in the PFAS story. Because communities that are angry and organized are communities that demand answers from companies and from governments that would prefer not to give them. The settlements reached with 3M and DuPont and other manufacturers in recent years, running to billions of dollars in total, have provided resources for water system upgrades in some affected communities. They have not provided anything that amounts to full accountability for the decisions that were made over decades to keep inconvenient research findings internal. The scientists and lawyers and journalists who worked to bring those findings into public view did so against significant institutional resistance, and the record they assembled is now part of the permanent historical record of how a chemical disaster unfolds in slow motion. It does not happen with an explosion or a spill that everyone can see. It happens quietly, over decades, in the spaces between what companies know and what they choose to share, between what regulators require and what they are able to enforce, between what science discovers and what policy acts upon. PFAS will be in the environment, in the water cycle, and in human blood for a long time. The generation that allowed this contamination to spread is not the generation that will see it fully resolved. What this generation can do is make the decisions that prevent the next version of this problem from following the same path. From discovery to deployment, to suppressed evidence, to regulatory failure, to planetary-scale contamination, to belated reckoning. The chemistry of the carbon-fluorine bond is extraordinarily stable. The institutions that allowed its consequences to go unaddressed for so long need to be less so. If this story stayed with you, hit subscribe and drop a comment below. Which part of the PFAS story surprised you the most? And make sure to like this video so more people can find it. There is one more dimension to the PFAS story that does not get enough attention, and it may be the most important one for understanding where things go from here. It is the question of how science communicates risk to the public, and why that communication so often fails until it is too late. The PFAS problem was not a mystery that eluded science for decades. The core facts were knowable and in many cases known. What failed was not the science. What failed was the path between the science and the people whose lives depended on acting on it. This is a pattern with deep roots. The history of industrial chemistry in the 20th century contains several examples of chemicals that were developed, deployed at scale, and then found to cause serious harm that had been obscured or delayed by the financial interests of the companies that made them. Leaded gasoline, which added lead to the fuel used in almost every car on the road for decades. Asbestos, which was used as a fireproofing and insulation material in buildings, ships, and vehicles until its link to a specific and devastating lung disease became impossible to suppress. Certain pesticides that accumulated in the food chain and disrupted wildlife reproduction in ways that Rachel Carson described in a book called Silent Spring in 1962, which is still one of the most important books ever written about the relationship between industrial chemistry and the natural world. In each of these cases, the companies that made the products knew or had reason to know about the risks before the general public did. In each case, the information was suppressed, minimized, or contested long enough for the products to remain on the market and the profits to continue flowing. And in each case, the people who ultimately paid the price for those decisions were not the people who made them. They were the workers who handled the chemicals, the residents who lived near the factories, the children who grew up drinking the water, the communities that had no power to demand different choices from the institutions that were making them. The PFAS story fits this pattern so precisely that it sometimes reads less like a specific event and more like a template, which raises the question that the history of PFAS most urgently demands an answer to. If this pattern has repeated itself enough times to be recognizable, what would it take to break it? Part of the answer lies in how chemical safety is evaluated before new compounds reach the market. In the United States, the default assumption under chemical regulation law has historically been that a substance is safe until proven otherwise. The burden of proving harm falls on regulators and the public, not on the manufacturers who profit from the substance. This is the opposite of the approach taken in many other areas of product safety, where manufacturers are required to demonstrate that a product is safe before it can be sold. Shifting the burden of proof in chemical regulation, requiring companies to demonstrate safety rather than waiting for regulators to demonstrate harm, would fundamentally change the incentives that have produced the PFAS situation and its predecessors. It would not eliminate all risk. New chemicals will always carry uncertainties that only become clear after years of use. But it would make it far harder to deploy a chemical family at planetary scale while suppressing evidence of its risks, because the obligation to investigate and disclose those risks would sit with the party that has both the knowledge and the financial interest to do otherwise. This kind of systemic change is slow, contested, and politically difficult. It involves rearranging incentives that are deeply embedded in how the chemical industry and the regulatory system relate to each other. But the alternative, continuing to discover after the fact that the chemicals saturating our environment and our bodies are causing harm that could have been anticipated, is not a path that leads anywhere good. The PFAS contamination that is already in the world will outlast the regulatory battles being fought today. It will outlast the careers of the scientists studying it, and the lawyers litigating it, and the regulators writing the rules around it. It is, in the most literal sense, a permanent feature of the planet's chemistry, present in the water that falls from the sky, in the rivers that carry it to the sea, in the blood of every living creature that drinks from those rivers. That permanence is the final and most sobering lesson that PFAS has to teach. What we put into the world does not always come back out. Some things, once released, stay released. And the time to understand that is before the release, not after.